Here I'm the last talk. And my name is Guannan, and I'm from Tufts. So this is joint work with Shangyin, Koushik, and Matei from Berkeley, UC Berkeley. So I'm going to have another talk about using algebraic effects to model the interaction with larger language models. And a simple way to interact with language model is really just through prompting. And prompting is really just doing those string manipulation. Right? Here I have an example to do sentiment analysis using GPT. Right? I have a system prompt specifying we're expecting a JSON format to give us the sentiment result. It's positive, negative, or neutral. And here I have the user prompt is to say just classify this sentiment as an input to the language model. Very simple, right? But this kind of way of programming language model is very not robust. It's also not very rigorous to specify the interaction with language models. And one way to improve that is to shift the perspective. Instead of just simply prompting the language model, can we program the language model? And one of a way to do this is using this DSPy framework. And in DSPy framework, it allows user to specify interaction. For example, here, doing the same analysis, I can define a signature for the interaction. There's sentiment signature extending the SigPy signature. And in this class, I can specify there are some inputs field, and there are also some output fields. And in the output fields, we just say, OK, once the output has to be positive, negative, or neutral. And at the end of that, we can call DSPy with predict, given the signature and the actual input to be classified. This seems all good. It's providing a good abstraction from prompting. But that's not enough. And because this predict function is basically a black box, the user cannot really customize or control how we are really calling the language model, right? So our idea here, so this is not enough to program language model. So our idea here is, again, using algebraic effects and handlers. And I hope the previous talk already motivated enough for you. So the general idea here is really the same. And though we can express effects, which declares what can happen. And we use handlers to specify or define how it actually happens. And to put this analogy here, we propose a sketch language called Pangolin. And the idea is to represent language model interaction as effects. And they are entirely abstract operations. And we can define separate handlers providing the interpretation of those effects. And next, I'm going to talk about several examples with this still hypothetical language, but hope to convince that this is a good abstraction for programming language models. So here, this is a program in Pangolin. And this is doing the same syntax analysis as I showed before. And here I define a function. This is this lambda function as an emotion classifier. It takes an argument, which is a sentence, to be classified. And inside of this function, I specify the specification, which really just saying, OK, what is the input? What's the type of input? And what's the type of output? They're both just strings, right? And we can instantiate this specification or this protocol with a given sentence, right? On the right, the sentence is really referring the actual argument of the string to be classified. And after that, we can call the language model with this LM. But here, the LM is really an effect operation. It's abstract. At this point, we're not giving the meaning, or we're not providing the interaction at this point. But then after we're retrieving the result with statement, we can return from this function. Okay. So here's a naive handler, right? And here we define the handler, and the handler has a pattern matching here, kind of like pattern matching, to say, OK, I'm going to handle this LM effect. So the LM effect has providing 3 arguments or into the scope. The first one is the specification, which provides a protocol of the input and output. And also, it provides the actual input to be used as a string into the language model. And again, there's also a continuation K here, so that we can resume back to the point where we throw or issue this side effect. And the first step is we need to format the actual string according to the protocol or specification into the language model. So we use this write function, and it's kind of parameterized over the spec and the actual input. So we get the actual prompt, which is a type of string used to be the language model. There's another primitive effect or native effects called the prim.lm, which is a function to really invoking the external language model, for example, using APIs or you can host the language model locally on your machine. And after we get the result, this is raw result, then we use this read function to convert it back or pass it back to the structured output we're expecting. Then with this output, we resume back using the continuation, and the execution continues to the point where we throw the exception or throw the expect. And then to use this handler, we use this handle with, given the actual emotional classifier and also the handler here. So this is really not doing anything fancy, but just adding another layer of indirection, right? But we can also doing something more on top of that. And in effect handlers, we provided this continuation k, and this k in our language is a multi-shot continuation, which means we can call this k multiple times. Okay? And here, I have a similar effect handler to handle this LM effect, but after I constructed the prompt, I'm going to use a map function to call this prim LM multiple times for n times. Okay? So n is a parameter given by this handler. So I'm sampling n times of the language model, the result. And similarly, I parse those outputs, all those outputs, using this map function again. So I have an array or a list of outputs from this parsed output. And eventually, I use this fold function to concatenate everything. And so the user will take n outputs from the language model. So another idea here is, on top of this, we introduce a further idea using selection monads and handlers for programming language models. And selection monads formulate laws inside of an effective program, and we can express search over objects through this choose operation. And handling selection monads can be combined with effect handling with additional loss continuation. And we will later see more examples about how that works. And this will be particularly helpful for specifying retry with rewards, and these rewards can be user-specified as well. And also to be useful, this is useful for scaling behaviors in LM interactions. And this idea about using selection monads and handlers has been applied to other machine learning or reinforcement learning tasks before. So here we're just really repurposing this for programming language models. So here are some examples. The first one is to do this best of n patterns. And here I have two effects, this LM effects and this choose effects. And inside of this LM effects, I'm calling this choose function. So this choose function or effect will be kind of forwarded to the handler in the second part. So this choose function is to say, OK, I have several outputs, but I want to choose the best one, right? And in the choose handler, it provides the LS, which are those options I can choose from, the normal continuation, just K, and also a loss continuation, which is KS. And I'm applying this loss continuation over all possible choices, right? And the loss continuation provides your score about those choices. That's a score. Then I can use this argmark function to get the best one. Then I'm just retrieving the best one from XS and resuming using this normal continuation. So in this way, we can sample several ones, but instead of returning all of them, I'm choosing the most with the highest confidence score. And that is specified at the lower part here. So here we have another primitive called score, and score is used to say, OK, the user wants to give a confidence or the loss or reward in this way. And this confidence score function can be either user-specified or even using another language model to do this. Okay. And here the example, I'm calling a language model for 16 times and only get the best one. Okay. There are user-specified way to do this feedback or loss. And one of the analogy here we're drawing is with assertion. Okay. And assertions in traditional programming is to say, I'm checking some value, whether they satisfy some condition, and it fails, the program just abort, right? Just quit. But here, we're using assertion to examine the result of the language output. But assertion failure doesn't really mean the whole program should terminate. It just means the feedback is low, or the reward is low, or the other way to say it is higher loss, right? So here, I have this choose effect to choose the best one, this result 1. And I have some assertions to say, OK, the result must be one of the positive, negative, or neutral. And I have also an error message here. And also, I have additional assertion to say the total length of the string should be less than 10, right? That's sort of arbitrary condition because we want to have shorter sentiment result. And in the handler, this assertion is also an effect. So we provide a handler for this assertion. And this assertion additionally provides different ways to do the retry mechanism. But here, the important thing here is this pred is a numeric number, and we can use score again to pass this feedback to the loss continuation. So here, the idea is we are selecting the output from the language model, which passes the most number of assertions. Okay. So this will be very useful to implement like chain of tree, this pattern. So the general idea we're exploring here is what is really a good programming abstraction with language models. And we propose this language called Pangolin and sketch its design in our position paper. And we use algebraic effects, selection monad, and handlers, and which provides a user customer way to interact with language models. And we think it's good to express many language programming patterns. And our future work is we need to implement this for language and also provide a formal semantics. Another interesting future work we're looking into is to see whether this pattern can provide better abstractions for building agents, like those agentic AI patterns, which involves loops or two-involved actions, which also can be expressed as side effects. So this is the end of my talk. I'm happy to take some questions.
Any question? Yeah, yes, please, come here.
First of all, thank you very much for the talk. It was really enlightening. I have a small question. Is Pangolin in any way or shape or form open source or available, or will it be made available?
We haven't get the full implementation. We only get a very tiny work in progress implementation. But at some point, we hope to open source it as well.
I see. Thank you very much.
Thanks.
Yes, please.
Thank you for the talk. So my question is, how do you see the usage of your language Pangolin? So the user should write this implementation of these handlers by themselves, or like you as a developer provide this in the language and then the user just uses them? Like, what is the case?
Yeah, ideally, some common patterns should be just provided as library, so user doesn't need to really re-implement it every time. It's kind of like the DSPy framework already provides like default interaction with language model. So we expect to do something similar there.
Okay, thank you. So a following question is then, so if your plan is to provide like some wrappers and some infrastructure to like build agents fast and all this stuff, there are pretty a lot of instruments also in more popular languages than Pangolin so far. So are you planning to compete with them? And if yes, then how? Like, what is your main advantage of using this language instead of any other instrument?
Yeah, I guess at this point, we're not really thinking about how to compete with other framework or languages. We're just exploring the design space using this idea about effect handlers and selection monad.
Okay, thank you.
Thanks.
Okay, any questions? Okay, let's thank you.
Yeah, thank you.